is class on hardware security. So, we shall in the last few classes we have been discussing about power analysis. In today's class we shall be trying to see how we can counter power analysis. Specifically, we shall be talking about a technique which is called as masking, which is a very popular strategy to prevent or protect against power attacks. And then we shall be discussing about some pitfalls of masking, and that will lead us to the introduction of a technique which is called as TI, or which is an abbreviation of threshold implementation. We shall be trying to look into some of the properties of TI and also see some possible constructions, and we will finally conclude with some experimental evaluations and results on a specific case study. So, to start with, how we can counter DPA. So, as we have seen, right, DPA or differential power attacks fundamentally works by exploiting the fact that power consumption depends upon the underlying data. So, there could be several strategies, and the strategies can be broadly classified into two approaches. The first approach, which is essentially very popular, is essentially by trying ad hoc design techniques, okay, which essentially with the objective of making power consumption of the device independent of the underlying data. For example, right, you can actually try to have a detached power supply. You can try to use logic styles with data independent power consumption. For example, you can try to bring in complementary logic. For example, in one case, right, if you are complementing with X, in another circuit you are operating on X bar. So, the idea is that if there is some net which is making a 0 to 1 toggle, there is some other net which is making a 1 to 0 toggle. Likewise, right, you can also try to bring in techniques like noise generators, inserting random delays. But the point is, right, most of these techniques are not essentially in tune with the normal CAD methodologies, and also, right, the methods are often costly. More importantly, these techniques being ad hoc do not guarantee against protections against these kind of attacks. So, therefore, right, it may happen that, for example, if we are talking about a complementary logic, although in principle it looks pretty nice because it would try to kind of pretty much make the consumption independent of data by making it constant, but then it would also depend upon how you are routing your design inside an ASIC. For example, if the two circuits, like the one which is processing on X and the circuit which is processing on X bar, are not routed in a very uniform manner, then it may happen to still, or it may still lead to I would say, like, it may still lead to non-uniform power consumption, which would still be dependent upon the underlying data. So, therefore, right, these techniques often are costly, and at the same time, do not give us an end-to-end security. But more importantly, right, these methods are not amenable to our CAD methodologies, and therefore, right, the designer in the very first place cannot try to develop or cannot develop his or her design with suitable countermeasures. So, this leads us to a second approach, which is essentially again with the objective to randomize intermediate results. But in this case, right, you can actually apply this at the algorithm level or at the gate level. So, therefore, pretty much you can implement them at, for example, the RTL level or the Verilog level, and therefore, these methods are more conducive and more desirable from the design point of view. So, therefore, these are again based on the principle that power consumption of the device processing randomized data is uncorrelated to the actual intermediate result. So, therefore, the idea, as we will see, is, right, it basically is built upon this idea that if we can randomize the internal information and essentially process, or when we are and do our computations on the randomized information, then the power essentially will be dependent upon the randomized data and not on the actual intermediate results. So, therefore, right, it would be statistically independent of the actual secret which is being processed. So, masking is one such technique, and it is a very popular technique which has been adopted widely for protecting against power attacks. So, principle of masking essentially is based upon the fact that no wire stores a value that is correlated to an intermediate result of the algorithm, and the process of converting an unmasked digital circuit to a masked version can also be automated, and therefore, right, this method is very popular and desirable from the CAD perspective. So, as we will see, right, in this kind of circuits there are two distinct parts. The one part which basically processes on the mask, and the second part, right, which processes on the mask data. So, the idea is that if you are processing on a data, right, for example, any intermediate value, you would typically try to kind of split it into two parts. One part which is the mask, which is essentially hiding your information, and the other part which is the mask data, which is essentially nothing but data camouflaged with the mask. Okay. So, we have to basically process both of them in an independent fashion, and we have to keep in very careful that no intermediate circuit is combining these two parts, because if we combine the mask along with the mask data, then the unmasked data is essentially exposed. And therefore, right, we have to do the computation in a manner so that the actual data does not get opened up during the computation. So, let us start with a very simple example of trying to mask a fundamental gate. So, this is nothing but the AND gate, and we would like to mask the AND gate. Okay. So, as we know that in the AND gate there are two inputs, like it is an input of A and B, and you basically give an output which is say Y or Q. Okay. So, Q is essentially a function of A and B, where A and B are your actual inputs. Okay. It could be like single bit values. So, in a normal unmasked data, we would basically do a processing on A and B, and therefore, the power consumption, since it depends upon A and B, would leak information about A and B, and that is what we have seen when we are studying about DPA and various versions of that. In a masked counterpart of this, or in a masked AND gate, what we will do is that we will basically take A, which is actual data, but rather than processing on A, we will basically mask A with a random value which is MA. Okay. So, MA is my mask. So, now once I for example, so one way of masking is by applying a bitwise XOR. So, we take A and we XOR it with MA, where MA is randomly a value for either 0 or 1. So, it is again a 0 1 random value. When I XOR it, I get AM. So, AM becomes my masked value and MA is called as the mask. Okay. So, essentially, right, I mean, you have got two parts. So, you have got, for example, this part which is essentially your mask, which is essentially randomly chosen. Okay. So, it is probably randomly chosen from a 0 or 1 value. On the other hand, right, this part is essentially what we call as the mask data. Okay. So, this is the mask data. So, now once you basically create this mask, likewise you also mask B by using the mask MB and creating the mask value BM. Now, your circuit should process on AM. Okay. So, it should process on AM. One second. It should process on these two parts. It should process on AM, BM, MA and MB. So, in no case, right, it should process on A and B. So, the idea is that A and B should never be processed together. Okay. So, therefore, right, we will basically kind of convert this function f into another function, say f hat, okay, where f hat basically processes on these masked values. And you can see I have also used another mask, which is essentially what is called as the output mask. Okay. So, the idea is that if you take this output mask and the circuit produces a QM, okay, then the final result is obtained by using this equation, which is nothing but Q essentially is equal to the XOR of QM and MQ. Okay. But note that in any case, right, if you have got a following circuit, you will basically suppose the following circuit operates on Q, but then the subsequent circuit also should be processing on QM and MQ. Okay. If I basically take QM and I combine with MQ, then again this data gets exposed, which is not desirable. Okay. So, that means, right, in the subsequent circuit I should again have a masked gate, which will again process on MQ and QM, but will not combine them. So, therefore, in no case, right, the mask data and the mask value or the mask should not combine. Okay. So, therefore, the entire thing should be processed in an independent manner or through independent circuits. Okay. So, let us now see, for example, how we can mask or how we can convert the AND gate into its masked counterpart. In a way, like in another words, right, we basically would like to see how to write f hat, right, given or knowing that f is nothing but the AND of A and B. Okay. So, that is what we will basically see subsequently. So, this brings us to this masked computation. So, basically, right, in a way what we want to do is we want to calculate A into B, but remember that there is an output mask, say MQ. So, we know that A is nothing but AM XORed with MA and B is nothing but BM XORed with MB, okay, and XORed with MQ. So, therefore, right, if I break it up, then this is essentially pretty much the computation which is done. Okay. So, you can see that it is nothing but we have basically applied a distributive property and basically kind of spread out the computations in this manner. So, note that in this computation there is no way, right, essentially we would basically what we are trying to do is basically we are trying to write the computation so that actual data A and B are not coming into play. At the same time, we have to also like slightly restructure this computation, because if I implement the circuit as it is as shown here in this particular equation, then it will again lead to a leakage. For example, you can observe that if I like combine, if I do the computation as it is like this, then this is nothing but Bm XORed with Ma, Am XORed with Ma, okay, and this data is nothing but A. Okay. So, therefore, right, although from the associativity properties, this is essentially I would be like I mean this is correct, but from the security leakage point of view, right, this essentially is not the correct way of doing the computation. So, basically kind of we have to rewrite, or we have to kind of implement them in a way so that in no case, right, we have got these kind of situations arising, that is the mask data and the mask should not combine together. Okay. And this leads us to a specific circuit which I will explain after this. And basically, right, I mean the whole objective of doing this masking is that, as we know that there are 4 inputs, okay, I mean we know that we actually know that there are 5 inputs, okay, they taking the output mask also into account, and each of them have got like 4 possible transitions like 0 to 0, 0 to 1, 1 to 0 and 1 to 1. So that there are totally 1024 possible input transitions that can occur. Okay. So, if you remember, like we previously in one of our classes we discussed about why AND gates leaked. Okay. So, there we saw that the average energy for E of Q equal to 0 and E Q equal to 1 are not equal. Okay. So, if you do the same exercise for the masked gate, you can essentially do it again, considering that the masked gate is a 5 input Boolean function. You can observe that it will turn out that the expected value of the energy required for processing of Q equal to 0 and Q equal to 1 will be identical now, okay, showing us that if the gate essentially performs one transition at one time, then there is no leakage. Okay. However, and that essentially means that these are protected against DPA under the assumption that the CMOS gate switch only once in one clock cycle. Okay. But we will come to a like a different argument so very soon, where we will see that if there is something which are called as glitches, where essentially the output of the gate will swing a multiple number of times before reaching a steady state, then still there can be a leakage. Okay. And the design, right, even after this protection can still be vulnerable against power attacks. Okay. So, at this point of time, let us consider that there are no glitch, okay, and let us assume that the gate is switching only once in one clock cycle. Under this assumption, right, we can prove that E of Q equal to 0 and Q equal to 1 will be identical, exactly in the same way we proved that it is not identical in the case of a normal AND gate, okay, proving that this circuit essentially should be secured against first order DPA attacks. Okay. So, therefore, right, as I said that, however, if I want to really achieve that, we have to implement the circuit in a slightly clever way, so that the mask data and the masked value, or the masked value and the mask do not combine together. Okay. So, one popular masked implementation is shown in this diagram. This is also called as Trichina's gate. Okay. I mean, if you, for example, so this is essentially a masked multiplier which has been shown, but in a similar way you can also think of a masked AND gate. Okay. For example, what you can think of is you can replace these multipliers by AND gates. Okay. For example, you can think that pretty much there are like 4 AND gates. Okay. So, these are the 4 AND gates which are together, and there is an XOR. So, we can basically start processing on the inputs like MB and MA. So, these are normal AND gates, okay, and you can take the output mask which is MQ, and you can basically combine it with an XOR. Okay. So, this is your XOR. So, therefore, this is your output mask MQ which is coming into XORing the output of MA into MB. Okay. And then again you take these 2 inputs which are essentially nothing but MB again. Okay. So, this is MB and this is AM. Okay. And likewise, let us complete this part. So, you have got BM, and this part is MA. Okay. And likewise these 2 parts are AM and BM, right. So you basically take these two part and you again combine this by an XOR. So there is an XOR here which is written over here. You take this part, so you can basically combine this by an XOR, okay, and again you take an XOR function, okay, and this is your finally this part, right, is your QM, because QM means, because QM is nothing but the XOR of Q and MQ. Okay. So this gate is also called as Trichina's AND gate. Okay. So so you can observe that the whole way, right, the principle of doing this computation is to bring in this MQ, which is completely unrelated to A and B at the very beginning. Okay. So you basically take two random values like MB, MA, and you XOR it with MQ, right, and you start the computation from this side actually. Okay. So therefore, right, once you have done this computation, you basically have got AM, MB, and then you are basically combining them with this part, and then you get this result. You basically combine with this XOR, and then finally you get this result. Okay. So so one should be, or one can be tempted. So basically you can say this is a very skewed circuit. Okay. So a possible temptation could be that I would like to like make this circuit is a very little bit balanced. Okay. And if you do that, right, you will always see that you can end up in combining the mask data and the mask value. Okay. And therefore, right, it is really a good exercise to see, right, that what happens if you try to balance this circuit. And it will happen that if you try to balance this circuit, then you are combining, say, a term like like for example, if I consider a balanced circuit, okay, so one may like by applying the principles of digital logic, right, for example, can end up doing this computation. So like I may be tempted to say like combine these two parts, apply an XOR, okay, here, and again combine these two parts, okay, apply an XOR here, and then I would like to apply an XOR here. Okay. So you can see that this basically makes the circuit more balanced and also probably reduces the critical delay of the circuit. Okay. But if you do that, right, then what you are doing, if you observe for example this point, okay, and if you observe this computation, say this is AM, this is BM, and this is BM, and this is MA. Okay. So again, right, this part is nothing but, if you take BM common, it is the XOR of AM and MA. Okay. And this part is again where you are exposing A. Okay. So therefore, right, this is a wrong wrong approach. Okay. So we cannot actually balance the circuit in this way, and therefore, right, finally I have got a circuit which is unbalanced, but at the same time, right, is essentially secured against first order leakage if there is no glitch in the circuit. Okay. So you can apply the same principle for realizing a multiplier, where you basically replace these AND gates by corresponding multipliers. So you can observe that like the cost of getting this security is significant, because in order to realize one AND gate, now you have got 4 AND gates and you have got 4 XORs. Okay. So therefore, there is a significant blow up in terms of chip area and other peripheral costs. Okay. But at the same time, right, this is essentially sound in terms of DPA leakage. So now we will see like that whether that's the end of the story or there are more things to be considered. Okay. So therefore, right, I mean we will basically consider masking and first order analysis, and here is a very interesting way of observing or taking a relook at masking. Okay. So in this masking designs, what we have done basically is that the intermediate variable x is split into two random variables x1 and x2, such that x1 XOR of x2 is equal to x. Okay. And assume that, again, if I like assume that the leakage is kind of modeled by the Hamming weight of x1 and x2. Note that now you are not storing x in a register, but the registers are storing x1 and x2 like the shares of x. Okay. So x has been broken up into x1 and x2, like we have broken up A into AM and MA. Okay. So there are two parts that you have broken them up into, and therefore the power consumption will essentially depend upon the Hamming weight of both x1 and x2. Okay. So if you just make a simplistic model like that and try to observe how essentially is the leakage, so you can see that here this diagram shows, or this table shows, that my input is say x, which is 0 or 1. If I break it up, if I write 0, right, then I can write the masks as either 0 0 or 1 1, because both of them XOR to 0, and likewise, right, I can write 1 as 0 1 or 1 0. Okay. So now observe what is the leakage because of this x. Okay, the leakage here is 0 because the leakage for 0 0, so that is 0. The leakage for 1 and 1 should be maximum, that is 2. Okay, the leakage here is 0 1, which is 1, and the leakage here is 1 0, which is 1. Okay, so now if you observe the mean leakage, right, essentially, so mean leakage means if I take the mean when the input is say 0, okay, the values here are like 0 and 2. So if I take 0 and 2, the mean is 1. Likewise, right here, if I take for the mean for the mean leakage for when the value is 1, it is here 1 and 1, so the mean is still 1. Okay, so therefore, right, from the first order point of view, like when we are just doing first order, when we are applying first order statistics, okay, that is when you are computing the mean and doing your like DOM or correlation power attacks, as we have seen, the mean is not leaking any information. Okay, and that is why, right, this is secured against first order, like, or potentially secured against first order attacks. But if you observe the variance, you will see that here the variance is significantly larger compared to here. The variance here is 0, where the variance is 1. Okay, and therefore, right, from the, if I try to do a second order analysis, this will still reveal, and like because of this dependence of variance on x. Okay, so this is important to keep in mind, that masking, right, in as we have defined, is essentially first order resistant but not resistant against a second order analysis. Okay, and therefore, right, we can still we would still like to improve the basic design if you want to protect against a higher order attack. Okay, so therefore, right, I mean this is so therefore the whole idea is that so let's see how we can develop the basic scheme. But before we go into that, right, what we will also try to see is what happens, like, so okay, so let us first of all define what is a higher order masking. Okay, so therefore, right, we as we see that our design is not secured against second order attacks. So likewise, right, it is of course not secure against a third order attack, fourth order attack, and so on. So therefore, if I generalize this in a dth order masking, what we will try to do is we will aim to randomize the intermediate sensitive data x by splitting into d plus 1 uniformly distributed variables. Okay, so like when we are protecting against first order attacks, we have broken up our input x into 2 parts. Okay, if I want to protect against a second order attack, we have to break it up into 3 parts, x1, x2, and x3, such that they XOR up to get me x. Okay, so in a generic setting, right, if I have got say x1, x2, x3, and so on till xd and xd plus 1, and I use some kind of operator to indicate how we are basically combine them. Note that the masking, right, essentially the way we have seen is that this operator is XOR, and this particular way of doing masking is called as Boolean masking. Okay, as opposed to this, there is another alternative way of doing masking where I apply for this operator, I apply a plus. Okay, so that is an integer addition, and that is called as additive masking. Okay, so each variable xi, so in this case, so you can apply both Boolean masking as well as additive masking. Okay, and each and you can observe the way in which we obtain the shares is that if I want d plus 1 shares, I will randomly choose x1 to xd. Okay, and then I will choose or calculate xd plus 1, I will compute xd plus 1 so that this equation is satisfied. Okay, and that you can easily verify that, for example, if this is XOR, what I do is I kind of randomly choose x1 to xd, and then I basically compute xd plus 1 so that their XOR is equal to x, okay, which you can easily get by XORing x with the XOR of x1 to xd. Okay, so therefore, right, each variable xi is referred to as a secret share, and the secret sharing can be done by randomly generating x1 to xd and by computing the value of xd plus 1. Okay, so now we would like to see that how we can really hide behind the mask. Okay, so given an input share, there are, I mean you see how we can apply masking. So to ciphers. Okay, so note that the ciphers can be typically having 2 types of transformations. It can have linear transformations or it can have nonlinear transformations. Okay, for linear transformations, actually masking is very easy. So because of this simple fact that if I break up x into the shares like x1 to xd plus 1, okay, then I know that because of the fact that the linear L is linear, when I apply L on x1 XOR so on till xd plus 1, that is equal to L of x1 XOR of L of x2 XOR of L of xd plus 1. So therefore, right, we can perform the linear operations on the masks. Okay, so you can actually break, when the moment you have broken up the input x into parts, you can apply the linear transformations on each of these parts separately, and you know that when you combine these results, you are getting the correct output. Okay, So, there is no problem in that case. So, likewise, but you know, like when you apply the process for a nonlinear transformation, then the process is much more complex. Okay. For example, right, when I want to compute say zx XOR of xy, where xy as we know is a nonlinear computation. So, therefore, right, one way of possibly potentially masking this is as shown here. So, I basically do z1 XOR of x1 y1, and in the other share I basically calculate z2 XOR x1 y2, XOR of x2 y1, XOR of x2 y2. Okay. So, note that, you know, like in this case, right, when I combine f1 and f2, then because of the combination of z1 and z2 I get z. Okay. And x1 y1 x1 y2, if I combine, right, I get x1 into y1 XOR y2, which is equal to y. Okay. XOR of again x2, if I take common, y1 XOR y2 will be equal to y. Okay. So, therefore, right, if I take y common, then I get x1 XOR x2, which is equal to x, therefore, I get xy. Okay. So, therefore, this is correct, but at the same time you should observe that the parenthesis here. Okay. This is very important, because if this ordering is not properly done, then again x2 y1 will combine with x2 y2, which will lead to the leakage of the information on y. And therefore, right, I mean, one should be very careful when you are applying, you know, like associativity in these particular cases. Okay. So, for example, here what we will do is that we will kind of combine x1 y2 with an independent data z2, and then I will combine it with x2 y1, and then I will combine the result with x2 y1, which is essentially trying to keep it secure against a first order attack. But as we know that this is not secured against second order attack, because the moment I combine the leakage of f1 and f2, then all my shares are leaked, and therefore the actual data is also compromised. Actually, this is not even first order attacks, okay, which is very unfortunate news. Okay. This is essentially not secured if there are something which are called as glitches inside a circuit. Okay. So, that essentially we will study up, you know, like in the next class, where we will see, right, what is the effect of glitches on these kind of circuits.